now by M, and that will be an M by M matrix, XP of 3. Okay, let me pause for question. Any questions so far? Okay. So the next step I'm going to do is we're going to use very similar architecture for the synthesis. Okay, for the other side. So I'm going to draw down here synthesis. Okay, so you have H0, H1, downsample. In the reconstruction, what do you have? Upsample and filter. Okay, so in the bottom half, you will derive similar architecture, but now for the synthesis. Okay, so let's do it. We have up by 2, up by 2, F0, F1. Okay? All right. So here is the question. So here is how we do this. F0 of Z, F1 of Z equals. Now, why do I have this as a row vector and this is a column vector? Because the operation here is serial parallel to serial, right? So if I imagine that this is U0, U1, okay? Then it's basically U0, U1, right? That product F0, U0, F1, U1 would give me that output Y. Okay? So instead of this is decomposition, right? From 1 to 2. I want to go from 2 to 1. The transpose form. Is that clear? Okay, so that's why we have a row vector instead of a column vector. So I want to derive the polyphase for the synthesis system now. Okay? So what do I have here? So let's call this the inverse 1. We'll explain why Z inverse 1 and 1. Okay? It's clear that we want to have Z inverse and 1. We can change it to 1 Z inverse. But I'll show you why Z inverse 1. Okay? So if this is Z inverse 1, how do I write it here? This is now polyphase form. What will be the first? F0 of 1. R. Very good. And why is F not even bottom? Here or there? There. So instead of a row, right now you have a column. Okay? So you have F0 even. 3 squared. And here is F1 or F1 even. Okay? Again, this is called Fp of Z squared. The definition for polyphase for F. And again, for any choice of filter F, I can always find the corresponding polyphase representation and form this matrix. Right? It's a one-to-one mapping. The difference here is instead of a row corresponding to one particular filter, here's a column. Okay, any question on this? Equivalent representation using polyphase. So we will copy this upsampling block here. Tell me what next. Is the matrix come first or the delay come? Matrix. How do I see that? Well, as before we said there's a vector here u naught u1, right? So I can imagine that there's a vector u naught u1 here. Okay? F naught times u naught, F1 times u1. And that vector will not be appear here. It will be here, right? The same vector u naught u1 will be here. So that vector will see the matrix first, and then the delay. Okay? So we'll draw the matrix first, Fp of z squared, and then the delay. Now, similar as in this case, where it is not efficient to implement a filter bank using filter and then downsample. Okay? We want to first block the input and then filter at low rate. It is not efficient to increase the rate and filter. So we want to somehow move this block to this side. And we can do this by the second, right? From here to, I'm going to use a different column, okay? From here to here. This is second noble identity. So let's move this block this side. What do I say? Fp of z. That is upsampling part, okay? So I say Fp of z. And then upsampling by 2. So let me put a box around the structure. This is a very important structure. This structure is equivalent to the cascade of these two, right? Cascade of this with that. That's your filter bank, right? Remember the filter bank? We use two branches to decompose, and then we use two branches to reconstruct. So if you cascade this together into a system, this is the filter bank. And we just show that using polymetric representation. And the first and the second noble identity, the equivalent form, basically a cascade of this and this. So are there any questions regarding what we have so far? No question. No question means I'm so good at lecturing. I'm not good at all, okay? It's either very, very good or very, very bad. So which one is that? Very good. Okay. The matrix is the same as finding the filter. Right? If I know the matrix, I can find the filter and vice versa. So what is the condition on the matrix? Such that you have PR. Is that condition easier to work with? So to give you any new insight to the problem. So any idea?
SP multiplied by FP must be an.
So what he says is this product has to be equal to 1. Why? Okay. Good. So those who know the answer, perhaps remember the lazy filter bank, right? That's the reason why I told you about this filter bank the day before this lecture. So you can actually use it to rewrite it, right? So what does the lazy filter bank look like? It is basically a way to block the input, okay, from serial to powder, okay? So you have here a way to block, right? You have a string number coming in, you form a vector representation. The vector coming out. And how do we reconstruct? You just deblock, right, interlace. So we have something by 2. That. If I connect these two lines together, and I know that if I block and deblock, it's perfect. Y of n is x of n minus 1. It's one delay. Right? Remember this one? Okay. And furthermore, what we have done last time is we said, okay, this can be identity. What if I introduce two blocks? And they are inverse each other. And in particular, we're using an orthogonal block, right? We use 1, 1, 1 minus 1, 1 minus 2, and so on. We use this choice to get the half figures. Right? You can show that they are orthogonal, so the transpose will be the inverse. Okay, and this is a half system. It's an orthogonal system. And you can show that if your basic building block is orthogonal, then you have orthogonal filter bank, orthogonal Wavelets, and so forth. Okay, so I won't have time to prove this. But the basic idea is that if the system inside here is orthogonal, then you have orthogonal transformation. Now compare this form to this form. What's the difference? They look very, very similar, right? HP is matrix, FP is matrix. In this case, they are both constant. Okay? But in general, if the product, right, if I can find FP of 3 and the corresponding inverse, FP of 3, if it is zeta minus L, let me use L hat, okay? It's a different L. Then you can show that if this is zeta minus L hat, I can prove it outside and we come to this structure, the lazy filter structure. Okay, so that would be the PR condition. The PR, right. The reason why, okay, the first reason why we use polyphase is that it allows us to build multi-rate system efficiently. So if you look at any multi-rate system in the world, system that convert from one rate to another rate. If you build a system that works in both the US, let's say an audio system, both work in the US and in Asia, the same rate are different, right? One is 4.1, one is 48.4. So there are different rates. How do you change the rate? We have to have some kind of multi-rate system in there. If you open up any of the systems that you buy, maybe a box inside that convert rate. Okay? If you look at a GSM network, cable network, maybe also a rate changing in there. Because for ADSL, you're combining multiple low bandwidth to a high bandwidth and so on. Okay, so open up any practical system. You will see boxes that have rate changing capability. And we never implemented like this. It is highly inefficient. Right? For 2 channels, you double the complexity. Because we filtering at high rate and we throw away information. It's not good. Imagine that you have 32 channels. It's very, very wasteful to filter at high rate and throw away 31 samples. Right? So the much more efficient way, the first use of polyphase is to implement multi-rate system efficiently. That's what we showed yesterday. Okay? The second use of polyphase is to allow us to have another way to represent filter banks. Now filter banks, you will see it also in cable network, representative cable system, ADSL, and so on and so forth. So I have both the analysis, decomposition, and reconstruction. Any cascade like that would allow we need a filter bank. Okay? And a filter bank is a cascade of this decimation and interpolation filters. So we can show that using filter bank, polyphasic filter bank, I can represent this operation efficiently. Right? Instead of filtering at high rate and throwaway information, I first block the input and I'm filtering it at a low rate. Right? Why low rate? Because we only have to filtering at every 2 samples coming in. Right? In the other side, when you do reconstruction, we don't want to insert 0 in between the sample, increase your memory, and then filtering. That's not efficient. First, we want to filtering at low rate, and then just interlace. This operation is free, right? This is basically indexing problem, right? There's no operation in here. This is just indexing. Okay, so this comes for free, that comes for free, and here we implement at a low rate, and here at a low rate. That's the first use of polyphase in filter bank, is to get an efficient way to implement a filter bank. Right? The second use is that if we can design a 2 system, a 2 polyphase matrix, such that they inverse each other, then you get perfect reconstruction. Okay, so what's the next question you should ask me? In the book, this is called condition. Okay, or say compound. All right. So I'm going to start with one example we know before. Tell me a simpler system that's a solvent that you know before. Okay. We're going to draw again half filter bank. And if you recall, this is 1, 1, 1 minus 1, 1, 1, 1 minus 1. So I'm going to draw again the polyphase form. One minus one is equal to 2 to normalize the norm to 1. One. And we know that the filter here is 1 plus the inverse, 1 minus the inverse, scaled by 1 over square root of 2. Right? Similar. Okay? How do I generate this? So I start with a length, so this have length 2, right? Length 2. Length 2 meaning that the filter H naught have 2 lengths, okay? 1 and 1, and so on. How do I have a longer length? How do I make it longer? How do I make it, let's say, length 4? What's length 4 look like? You have 1, you have the inverse, you have 2, you have 3, with some coefficient, right? That's length 4. 4 coefficient, 4 times. How do I go from length 2 to length 4 using this? So think about it, I'm going to draw, okay? And you can tell me the solution after I finish drawing. I'll call this block U naught. This whole thing. Can I add U1? That's orthogonal, that's orthogonal. The whole thing is orthogonal. I can invert. Right? If this is the case, how do I invert? If this is orthogonal, that's orthogonal. How do I invert? What is the first block here? That's U0, U1. U1 transpose, right? Then you have U0 transpose. You have this equalizing. So maybe I could cascade another block U1 which is orthogonal. Why orthogonal? Because I want a orthogonal to the bank. And would this give me a length 4 system? Yes. A show of hand for yes. Would this structure give me a length 4 system? Who thinks yes? Who thinks no? Why? Why not?
I think U0 is length 2, U1 is length 2. So the convolution would be 3.
Okay, so I add another one. Now give me length 4. Okay. Think about it. What is that product? What is the best way to represent a cascade of orthogonal system? What's orthogonal look like? That's the rotation, right? Right? Rotation by theta. Okay? Rotation by theta 0, theta 1, theta 2. What is the combined rotation? Theta 1, theta 2, theta 3, add together. So this can be represented as one digit U. Right? And it's basically the sum of the 3 rotations. So you back to this case, general case. So nothing has been done so far. Okay? You back to the square 1. Length 2, still length 2. With arbitrary coefficient here, okay? It goes down and side. And nothing can be changed. If you do it to infinity, you still have length 2 system. Is that clear? Because rotation by pi over 3, pi over 2, and so on. Just a rotation by sum of this angle. Right? You can change anything. So how do I solve this problem? Meet in the middle. You need delays, right? If this system is a constant system, you always have length 2. Is that clear? If it's a constant system, your polyphase matrix will be a scalar 2 by 2 matrix. You always have length 2. You need some delays in here. Okay? The delay will change by a factor of 2 and make it 2 to 4. Okay? So where do I put delays in there? One? Because 1 go to 2, right? So I put it in both of them? Will this work? Okay, I see it. Yes? Any support? Yes? Yes? Okay. It will go to length 4, but that's a problem. What's the problem? This is not the most general way. How do I prove that? A matrix. Matrix too complicated. Let's prove a delay for now. Okay? If this is the inverse, can I move it over here? Sure. Right? A matrix times the inverse I is the inverse I of that matrix. Right? And I move both this over here. Can I move them out here? Yes. So z to minus 2. So this problem is exactly the same as the other one with z to minus 2. So you have 0 here and 0 there. You basically shift it by 2. That's not good. Doesn't work. So how do I fix it? You understand the problem? If I have both as the inverse, I can move them to this side and move them out from z to minus 2 back to the old system. Shift it by z to minus 2, 0, 0. That's not general. How do I make it? How do I correct this problem? What if one of them? That will work. Right? That's allowing you to have, so your HP of Z, you have the constant and the delay in there. Okay? That delay gives you z to minus 2, z to minus 3. So I did this exercise for you later on. You can say, u0 and u1 is cosine theta 0, sine theta 0, minus sine theta 0, cosine theta 0. That's the rotation angle, okay? Here is cosine theta 1, sine theta 1, minus sine theta 1, cosine theta 1. And it's the inverse. You can find the corresponding orifice matrix here. And the turns out that matrix will have 4 coefficients instead of 2. That's give you a length 4. Okay? So I will not discuss this in detail. But you can go home and try it out. C0 stands for cosine theta 0. Cosine. Okay? This is sine, C. Okay? Cos, sine, sine. Okay? Alright, so this is HP of Z. How do I find corresponding inverse system of Z? This is u0, that's u1. I'm going to take inverse of this system. Okay, so how do I inverse? Invert this block first. Right? So u1 transpose. And that product will be I. It's gone. How do I invert that? What is the invert of 1 Z inverse? How do I invert 1 Z inverse? 1 Z, very good. This is not a trick question. Z. Right? And then do not transpose. That's correct. Right? Now, this is any question so far. So that's how you find FP of Z, and you're done. Okay? Now, what are the problems here? One small problem is that this is not causal. Right? How do I make it causal? Shift it by 1. So instead of 1 Z, how do I shift it by 1? What if I Z inverse? Let's make it Z inverse 1. Okay? So in the order up here. And what is FP of Z? FP of Z for this example. Z to the negative 1. What is L hat? For this example, I have a Z inverse here, Z inverse there. What is that? 2, 1. Right? Because this and this are identity. You have Z inverse, Z inverse. This and this identity you can put them out. Right? So Z inverse 1. So L hat 1, L is 3, and you have rank 4 system. Okay? So in general, you can build a orthogonal filter bank very easily. All you have to do is cascade a block with delays like this. 1 Z inverse. Orthogonal matrix. 1 Z inverse. And so on and so forth. Okay? So let me summarize it in the other board. Okay? I want to summarize orthogonal filter bank. So in general, we have the inverse, 2, we have orthogonal matrix U0, the inverse, U1, so on, right? The inverse, U of L hat. It can be anything, right? Depending on how many blocks you have. Okay? So you stop at 1, you have rank 4, rank 6, rank 8, so on and so forth. Reconstruction is very, very simple, right? Reconstruction would be we have U transpose L hat, and you lay up here, so on. We have U0 transpose by 2. How many delay do I have here? L hat 1. Minus 1? No, L hat, right? If I stop right here, I have 1 delay. So L hat. So this product will give you zeta minus L hat. Okay? So U, UK, cosine theta k, sine theta k, minus sine theta k, cosine theta k. That's how you build a general orthogonal filter bank. Just by cascading orthogonal matrix. Right, from here to there. It's orthogonal, it's guaranteed orthogonal. Such that you have good filter, right? You want H to have a good low pass filter and good high pass filter, and so on. Applications say that the way I use this filter, it will be composed by signal into low pass range and high pass range. If these filters are not good filters, then I'm not doing a good job. Right? And you can show that if I choose this arbitrarily, the filter will not be very good. So that's a design question of how to choose the filter K such that you have good filters. Okay, that's one good, but it's not the most important one. So that's a good question to have, practically. But in theory, I'm looking for theoretical questions right now. Computation, I know exactly how much computation, because I know how to implement this. I know how many of this guy, I can count the number of multipliers. Okay, so if somebody gives you a structure, right, and say that if I choose this theta k, I'm guaranteed to have a orthogonal filter bank. So given UK, given theta K, I get orthogonal filter bank, right? Orthogonal filter bank is H0, F1, F0, F1, right? And you can prove it from here. As long as theta K, as long as you're using this form, for arbitrary theta K, this appears orthogonal, and therefore the system is orthogonal. This is the simple proof. That is a difficult one. Right? What does it say? It says that is this the most general system you can think of? It's not useful to give me a system that does not cover everything. Right? Because if this is not general, I might not be able to design good filters. Right? Because, okay, so you have to provide if and only if, right? You have to show that it's not only give you orthogonal filter bank, but it's the most complete structure. So, completeness. Completeness means that it's the most general structure. In other words, if somebody not using this kind of design, right? Maybe using half band design. Okay? Give you a 4 filter that's orthogonal. And you can do that, right? Using half band, you factorize this such that F0 is H0 flipped, and you know H1, F1. Take those filters, it's just orthogonal, and I'm giving that to you. I will say that. Can you find me a unique set of theta K that represent those filters? If the answer is yes, then your structure is complete. And therefore it's a most general structure. If the answer is no, this is not useful. Right? So how do I show completeness? How do I show this? This is easy. How do I show that? You have to come up with a way to synthesize. Meaning that we start with the filter here, we're going backward. Right? So we start with a set of filters, we're going backward. Synthesize this block. Okay? If this blank 4, we go through here, blank 2, and then blank, and we complete. If this is blank 6, we go to blank 4, blank 2, and we're done. So on. Okay? So I'm not going to, it will take 15 minutes to derive the synthesis. But there is a synthesis procedure in the book that discusses how to go from a general orthogonal system, peeling off or synthesize all this block. Every time you're going from here to here, you want to reduce blank by 2. Right? Go 6, 4, 2, we're done. 8, 6, 4, 2, we're done. Right? What else? You want to reserve orthogonality. And that's easy because as long as this block is orthogonal, then you're done. Right? So the synthesis procedure actually discuss how to find this block such that every time you go peeling up a block, you're going back, reduce by 2. Okay? And the third guy of this system is a complete system. Question? Okay. what I'm trying to do here is, I'm trying to give you the applied math derivation for perfect construction. Okay, so you see many ways to do perfect construction. Alright, so let's see how do I start. Let's look at the filter line, okay? Let's call this C, D, apply math, we use C and D. So I want to be consistent with all the formulation that you see in the literature. So C will be the low pass filter, D will be the high pass filter. The reason why they use C is this filter is for coarse approximation. Coarse approximation is low pass. Okay? D is for detail. The detail of the signal appear in the high pass. So that's why I go C and D. So coarse approximation and detail. So X of N, C of N, D of N. Now, apply math. Doesn't know Fourier transform, doesn't know Z transform. So all the derivation here is based on time domain. And go CC time right now. So what we'll do next is I'm going to take a vector C at X. We know the coefficients for C and D. We're going to see what happened to this output. Okay, let's call this is U0, and this is U1. U0, assuming that we have infinite length, scenario. So you don't have to deal with the border either. Okay? So here's U0 equal to, how do I represent convolution in the time domain? Who remember convolution? U0 of N. Let's say C has length 4. Okay? So it becomes easier to work with, right? Summation C of K, X of N minus K. So you have C of 0, X of N, plus C of 1, X of N minus 1, and so on, right? It's a sum of flip and shifted. Okay? So you see that the C0, C1, C2, C3 have X. Okay? X of N and minus 1 and so on and so forth. So what do I say? I see that it will be C0, C1, C2, C3. Okay. That, this exactly is this, okay? That make it easier to see. Right? If you have longer line, let's go this way. Okay? So C0 N, C1 N minus 1, minus 2, minus 3, and so on. That's convolution. This is a matrix representation of convolution. Have you seen this before? Maybe, right? Most of the time you see convolution like this in Z domain, but you don't see it as written this way. That's how, apply math. That's how mathematicians write. Okay? They don't know convolution. Okay. What is the next sample? How do I write the next sample? Shift to the right hand side, right? It will be C0, C1, C2, C3. Because the next one, C0 times this one. Okay, and so on. So you can show that it is basically a total matrix. Okay, it's a band couplet matrix vector. Okay? Let's look at U1. I'm going to cascade the two together, right? So the top half is U0, second half is U1. They work on the same vector x, right? And they actually align in time. So exactly the same format we have here, copy down, only change from C to D. So yeah, line by line, we copy exactly the same thing. D3, 2, 1, 3, 2, 1, 3, and so on. Okay? Let's look at V, 0 to V1. How do I represent V0 and V1? What happened? What's the difference between V0 and U0? If U0 have length, 10, what is V0 have length? 5, right? So I see that there's a reduction in size. Reduction in size, how do I denote here? Suppose this is the 0 time, right? That's the one I say, okay? If this is U0 of 0, equal to that, okay? That's the one I say. I say V0 of 0 is U0 of 0. So I have C3, C2, C1, C2. That is the 0 time. What is V0 of 1? V0 of 2. So we are picking this row. We skip this row. We pick this row. That's downsampling in the time domain. Right? We're just picking, one here, and then throw away that, next one, and so on. Right? And that's basically just selecting every other row for that matrix. So now I have C3, C2, C1, C0. Because I'm skipping one. So now instead of a single shift, I have double shift. And that's downsampling. You see a matrix like this, with shift of 3, that's down by 3. Okay, so downsampling in the time domain, you can see it right away. And exactly the same thing when you copy this, exact form, replacing C, D. D3, 2, 1, 0, 3, 2, 1. L. So what we have done here is, I have written this. I see V0 D1 apply as a matrix compact, right? So V0 D1 as a matrix compact. Okay? What L here is a cascade of a complete matrix C, the downsampling operation. I know how to represent L and C. Right? And I can sum this as one big matrix, if I wanted to. Okay? You can think of this as that's a vector right here, right? That's a vector. That's also a vector form. That's a matrix, right? So you have a matrix, a vector V equal to a matrix of vector X, right? So vector V, which is a cascade of V0 V1, right, equal to a matrix times X. That matrix is over here. right? Now, in this way, it's easy to see. What if I want a orthogonality? What do I need to do? I want to make this matrix orthogonal. Right? If this matrix is orthogonal, I know how to invert them. I just transpose it. Okay? So I want to discuss after the break, okay, how to make this matrix orthogonal. If you can do this, then the invert is just a transpose, very easy. We will skip the inversion and leave that exercise to go home and do it. Okay? So the next topic to do after the break is given this matrix, which depends on the filters. Okay? And this matrix is a Topic, Bennett Topic matrix, shifted by 2. How do I make this into orthogonal? You can do that, I'm done. Okay? And that depends on how to do C and D. Take a break. Which means that it is orthogonal with norm, unity norm. Okay? So how do we design, how do we choose C and D such that this matrix is to be orthonormal? How do I make it orthonormal? You want norm of this vector equal to 1, right? Tell me the condition. You want C0 square, C1 square, C2 square, C3 square to 1. Right? And this have the same norm as this, and so on. You want exactly the same thing for D. D0 square, D1, D2, D3 to the 1. So that takes care of the normal part. We normalize the normal 1. Okay. How do I make it orthogonal? So you have 2 vectors, okay? How do I make them be orthogonal? Inner product equal to 0, right? If you take inner product of 2 vectors, what do you get? You have C0, C2, so C1, C3 equal to 0. Okay? So C0, C2, so C1, C3 equal to 0. And the same for D. Yeah, D0, D2, so D1, D3 equal to 0. Now this is the case for a length 4 system. If you have length like 6, so on, then you have an additional condition, right? If you have length 6, you have overlap, one more overlap, so on. So let's stay with this example, and we can generalize, find a generalized form later on for arbitrary length, given length. So how do I solve this problem? How do I choose a vector such that they satisfy this 4 condition? What do we know about C versus D? What do we know about C and D? Are they similar vector or very, very different vector? One may be a low pass, right? Because this captures the fourth approximation, the low pass version of the signal. And this has to capture the details. So one is low pass, one is high pass. Okay? So we know that D and C could be related somehow. If C is low pass, D will be high pass. So tell me if I know C of N, and C is low pass, how many ways can I get a high pass? I'm going to use this bracket, the same at this, okay? So interchangeably. How many ways can I make a low pass become high pass? In the time domain. In frequency, how do I make it low pass become high pass? You shift by pi. Okay? Shift by pi, this becomes what? What does it look like? Series of minus n. That's it? Minus 1 to the n. Would that work? Would make it high pass, low pass, right? Now, if I plug this into here, see what happens, okay? Erase this D and see whether this choice will work. So now, can I make it to be causal? I want to shift by 3. So make it causal. Okay? So D0, which is right here, equal to C3. D1 equal to minus C2. And then give me C1 minus C0. Okay. This row here is basically the D factor, right? D0, D1, D2, D3 with this substitution. Okay? Oh, is this enough? Sorry. Is this enough to be orthogonal? Are we missing something? We look at this, looking at that. We are not looking at this row, right? So we need to have C0, D0, C1, D1, C2, D2. So I have to have D0, D0, C1, D1, C2, D2, C3, D3 equal to 0. Also. Now this deals with a C, that deals with a D. But we haven't discussed C and D. Right? It has to be satisfied. So not only this, but I want, you know, this and this also. So I need C0, D2, C1, D3. So it's kind of complicated, right? There are many different conditions. We'll take a look at this row and this row. This row and this row. That's the C and D row, okay? That's this one right here. Are they orthogonal to each other? Yes. C0, C3, C0, C3 with minus sign. C1, C2, the minus sign C1, C2. So you can show that if I flip it this way, then these two rows will be orthogonal, these two rows, and so on. Okay? How about this and this? That is this one right here. So we show that this is orthogonal, right? How about this one? That this and this. Are they orthogonal? Yes. It's C2, C3. Minus C2, C3. Also, so by choosing it to be like this, I can take care of the cross orthogonality condition for C and D. Okay? I only have to deal with one of them right now. If I choose this way, I only have to deal with either C or D. Because the cross one will be orthogonal. With, we're going to call it star 1, this is star 2, and this is star 3. Okay? There are 3 groups. The first group is dealing with orthogonality and orthonormal within C. Star 2 is dealing with orthonormal condition on D. And star 3 is a cross orthogonality. Okay? And star 4. Star 4 will take care of star 3, right? Can show that. If I choose star 4 related D with C this way. One is the triplet, the other one is frequency. Then we'll show that this is guaranteed for this example, and you can show it in general. Okay? And you can show that star 4 with star 4, you only have to look at star 1. Because star 2 will be guaranteed also. If star 1, if you can choose C, satisfy star 1, then D from this relationship will also satisfy star 2. Okay? So the only thing left after this choice in star 4 is how to find C as satisfies this. Is that clear? Okay, let me summarize again, okay? Let's come here. We recognize the analysis for the bank. It's nothing but a matrix operation on the vector X, right? And that matrix operation is basically the matrix L, which is the one up here, and B, which is the one down here. And that can be grouped to one big matrix. Okay, so if you write this in terms of vector form, the question of finding the two filters, so starting on an orthogonal decomposition, is equivalent to finding this matrix that is orthogonal or orthonormal. Is that clear? Okay. And how does this relate to C? It's basically a band-public matrix. Double shift. Double shift because now sampling by 2, right? So if this is the orthonormal condition, right, that will filter. One will be dealing with the C, right? One will with the D, and one is a cross between C and D. Okay? So the next question is, how do we choose D and C? Right? We go back to what do we want? What is the objective of this decomposition? The objective is we want to capture the coarse approximation, the low pass, in the first branch. We want to capture the second, capture the details, the chain, which is high pass, in the second branch. Right? So is there a way to relate C and D together? If I know how to find C, can I find D in the related set? And we know how to do that, right? We can shift by pi in the frequency domain. In the time domain, basically n replace with minus n, pi becomes e to the j pi to the n. E to the j pi is minus 1. Right? There's 3 here, you have to make sure it is causal. Because both our system is aligned at time 0. Right? So using this particular choice, you can show that that the cross orthogonality condition will be satisfied. You can show that 2 and 1 are equivalent also. Okay, so the only thing left is we're going to choose this and we're going to do this. Is that clear? Okay, so I'm going to write this again and look at the condition for that. Tell me what does it look like? That's the summation, right? If we have C of n minus 2k equal to delta k, would that be okay? Let's take k equal to 0. When k equal to 0, what do we have? This equation, right? When k equal to 0, you have Cn squared. And delta k is 1. Right? So you have sum of the C squared equal to 1. Okay? When k is 1, what do you have? You have Cn and Cn minus 2, right? So C3, C1. C2, C0. Right? Okay? Equal to 0. Now, you can see that if I have length 6, right? I will have exactly the same thing. But k range from, this is k from 0 to 1. Right? For length 4. If I have length 6, what's the range of k? 0, 1, 2, and so on. So I can see that the exact formula I have here will carry through. It doesn't matter of how many k do I need to enforce. Right? To enforce. Is that clear? So that's the the most general way of writing this, right? And this come about because of the orthonormal condition on C. Okay? Have you seen this before? No. Okay? You sure? Okay. I claim that you've seen this before. So let's think about what this means. Okay? So let's use Z transform now, okay? How do I take Z transform? Okay. This is C of Z. What is that? What is that? That's convolution. Right? That's convolution. What's that? That's convolution. Can it be the same thing, right? Convolution downsample by 2. Okay? If I call this is P of n. Okay? Now what does it mean? It means that I have C of Z. How do I explain this? Okay. Let's define P of Z is C times C Z inverse. Okay? Can you tell me what does P of n look like? That's convolution, right? One would be flip of the other one. How do I write? This is C of n, C of k, C of L, C of L minus n, right? What does P of 2n look like? C of L minus 2n. Okay? Okay. Okay. And 0, right? Minus 1, still 0. 2, minus 2, still 0, right? That's what I'm plotting cube of k right now. And that's just delta k. Okay? Let's map this because what you see here is this k is by factor of 2. So if you write this in the non-subsampling form, you will have 1 here, this will be 2, this will be 4, that's minus 2, That's -4. So basically, this is nothing but a half band condition. On P of Z. Okay, P of Z is like this. You only increase the index by 1. Comparing this one with this one, index increased by 2. Because in a different scale. Basically, we're saying that P of Z for every even index is 0. Okay? Equal to 0. This is basically a half band condition, right? And we don't care what is at 1 or -1 for P of K. Okay? At 3 and -3, and so on. So this is basically the half band condition on the product filter. This is your H0, that's your F0. If you recall how the H and F are related, I just stripped. Okay? So you see it here also. Let me think about another way to explain it. Next time. It's basically the equivalent condition of the normal on the matrix itself. It's basically a half band filter condition on this product filter. Question? We will only talk about dyadic wavelet. Dyadic is for 2, based on 2. Okay, di is 2, right? Okay, so dyadic wavelet is when you have downstreaming by 2, and so on. Wavelet is basically a cascade of filter line. So we want to have low pass, power by 2, high pass, power by 2. We're going to cascade this on the low frequency. Okay? If we continue on doing this, you have a wavelet. I'll discuss why do we iterate on low frequency. That's a wavelet. Dyadic wavelet. It's built on a two-channel filter line. And the reason why we iterate at low frequency is that in most of the practical signal, it have more energy at low frequency. So that's why we iterate at low frequency to decode it on better and better. That's a good thing. And you can iterate this, further, right? And a shorthand notation for this is basically I can do something like this, right? If I do this, you know that this is basically a two-channel filter line. The analysis, right? It consists of H0, H1, and downstreaming by 2. Okay? And we know how to reconstruct, right? All I can do is reconstructing this branch, and then this, and that, and that. Okay? So reconstruction is simple. Basically, this. Okay? So how does the signal look like if you do this? Let's see. Okay, good example. All right. So, can you describe for me this wall? How do you describe this wall in Vietnamese slide?
This one is on and flat.
It's kind of a flat, right?
Flat.
And what color? Like yellow, white, yellow, right? Good. Look, can you describe this wall?
Height about
Okay. How about Tuấn, can you tell me what you want? No, not Tuấn. What's your name? Then can you tell me what? Describe this wall. Yellow, kind of flat. Do you see this? Do you see this? See more structure, right? Can you put your hand in here and tell me what? How do you guys know? It's not flat at all. It is very, very non-uniform, right? You have small bumps and so on and so forth. Okay? If you believe me, basically you can look at the object, right? Far away. And at this length, it's basically a yellow wall. It's flat, it's perfectly flat, okay? At half the distance, I can see dot right there, but it's still flat. I can see some dirty mark out there, okay? At 1/4 of the distance, I can see more structure, right? I can see that bump actually have some direction going down, right? This line here, there's a line goes up like this, a crack, and so on. But I'm on the wall, holding, touching it. It's really, really, really non-uniform. It has small bump, right? Everywhere, okay? So that's wavelets, okay? Wavelets allow you to look at the signal and very, very far away. So this is far away. Okay, you can see that this is a low pass approximation. It's where you are so far away. All you see are low pass structure of your object. When this right here is a little bit closer. Okay, you are now half the distance from the other distance. You see a little bit more. Over here, closer, bright, okay? You what I mean? Half distance, okay? And then here you are at the source. You can actually see. If you sample, right? This is your sensor, right? You sample, you will see, 1 and 0, all that stuff, okay? So you see that wavelet allow you to look at the signal at various resolutions. So there's a notion of multi-resolution. Resolution is how far you're away from your object, right? And this has multi, 1, a half, a quarter, an eighth, and so on and so forth. That's wavelength. Okay, now this is very, very efficient if you have low pass signal. Right? If this is a highly low pass signal, there's no need for you to do anything here, right? All you can do is saving this signal. So if you do compression for person that's always me, in the 40s, I need classes to see. I can no way of saying any structures there. But there's no need for you to send me very high resolution. You can send me this resolution. That's good enough, right? If you need to, display a wall very close by with structure, and you need to send everything. Okay, so this way allow us to choose which resolution to send and how much to send. Okay? That's multi-resolution. Now, the choice of a filter, okay, it basically will dictate how well you capture the low frequency signal. If you use a very, very bad filter, right, at low pass and high pass, then you'll not be able to record the signal efficiently. Okay, so the better filter we use, the better we can represent the signal. Okay, so that's the motivation for wavelength. I'm going to use some of the transparency to show you what does it look like in real signal. Okay. And you can choose different wavelengths to use, and you can compare, the effect of the trade-off between wavelet and wave transform. And this is free; you can download it from the web. So So what I can do is I can load in a signal, right? This is 1D, I'm loading a sound file. Let's say you can look at any sound file. Okay, this is the sound file, and I'm going to listen to it. Okay, so let's listen to it. And what it's saying here is 8-bit. I'll play it at 22 kilohertz. Second.
You call back.
It said you call back, right? So
You call back.
you call back. Okay, it's very low frequency, and you see that there are some static here. You can hear it. Basically, you call back. Low frequency, right? Let's hear it again.
You call back.
Okay, so I'm going to apply a Wavelet transform on this and see what it looks like and see how it sounds like, right? So we're going to have transform. That's a Wavelet transform, and now you can have. So basically, you can say, graph 1 is this graph, and you can choose level. I want to choose one level for that. One level is one branch, right, going like this, okay? From 1, that's one level. Okay? One decomposition. That's one level. I'm going to use half, which is the simplest, not very good, but it's sufficient to show that what happens when you apply a transform. And you can use Wavelet, you can use lower sheet, which is what we have discussed before, or you can use the 97 tag Wavelet that's used in compression. The first half, that's low pass, that's high pass. Just concatenate the signal together. So you see that the first part of that is this signal, and the second part of this signal. Okay, so I'm going to play it. Right there, audio. I'm going to play it at the original rate. Okay, 22 kilohertz. Let's hear it again. Okay, so what happens? What happens is that, relatively speaking, right, that bandwidth is half the other bandwidth. So what is the sampling frequency that we need to play back? Half of it, right? If I not want to play back at 22, at 11. So instead of 22 kilohertz, I want to play back now at 11 kilohertz. Let's see what happens.
You call back.
You call back.
Okay. So do I need to retain this part at all? No. This is fine, right? You can still hear. You call back. Let's hear it again.
You call back.
You call back.
And you recognize that the high frequency, the static is reduced because you do a low pass filter, so it's even better,
You call back.
right?
Call back.
Now let's do a wavelet again, but on 2 instead of 1, right? So wavelet, 2 level. Now what do we expect to see? In 2 level, I'm going to take this guy, not 4, 3. Take this and do this. Right? So I have this, the first part, split into a quarter and a quarter. That's a half. So I expect to see this part unchanged, exactly the same as before. Right? But this part will be decomposed into low, high. Is that clear? Okay, move on. Do it again. This one, on the original one. Okay, so this is the original, right? That's a 1 level, and that's a 2 level. So to compare 1 level and 2 level, what do I see? I see that this part is the same, right? But now display at this different scale. So it's kind of small, right? And this part here It's decomposed into low frequency and high frequency again. So let's play this again. Right? Let's see. It has low frequency, her hands, her face, the background is low frequency. Low frequency in image is an image area with constant energy, right? Constant intensity. There's no a small change. Okay? Edges. You can zoom into this area, you see there's a lot of edges. So if I zoom into here, and I go to the area around her hand, I can zoom. And you can see that when you zoom in, you see all this directional information. That's high energy. So the way that you scan an image, right, go from left to the right, what do I see? I see this. Right? Going from dark, going from bright to dark. Okay? From bright to dark, and so on and so forth. You have this signal. What's that signal? That's high pass. Right? So this particular image has a lot of high pass signal. Here also, you look at the area around the tablecloth. Right? It has information going this way too. So it's both directions. Okay? So this is relatively speaking a hard one to compress. Right? And if you look at the area around the table leg, this is the highest frequency, right? Because going from very, very bright to very, very dark. And the change is very, very sharp, right? So that's the highest frequency. So in compression, those are the areas that you make mistake. Okay? Because in compression, right, after this decomposition, what you do is you would truncate this, right? Quantize it. Okay? When you quantize this, you make mistake. Right? Quantize is going from a very dense sampling to a very coarse representation. That's quantization, right? You quantize, you make mistake. And you make mistake on the high frequency one. And that's where we see the artifact. The artifact is basically a high frequency. Okay? Now, the difference between 1D and 2D. Let me zoom into here. Okay? Let's look at we're going from this original to this representation. And you see that what happened is that the size reduced by a factor of 2. Right? So you are doing a decomposition on the row. So what happened here is, and you repeat on the columns. Right? So each direction is reduced by a factor of 2. Okay? So you have low pass, high pass. Low pass, high pass. Right? So this part here is low pass in both X and Y. Right? This is low pass in this direction, but high pass in that direction. And this will be the high pass in both directions. Right? So in this image here, there's a lot of horizontal. So that you see that some structure in here. Okay? Less vertical and diagonal is so small you cannot even see. But if you zoom in, you can see. Okay? So I'm going to zoom in the area around. What should I zoom in? This area. The chair. You can see that the pixels are very, very big now compared to the other pixels. Let's do one more level. Go back to the small graph. Apply transform. 2 level. And 3 level. Very, very small. Okay? So what I'm going to do next is I'm going to zoom into this area and see what's going on. Right? I'm going to zoom in the middle. play this. Compare this with number 1. Then go back and forth. Okay, 1, 3. What do you say? Okay. Well, 1, 4. Okay, that's a good one. Go back 4 to 3. Let's do 3, okay? To 2, I'm going to zoom this one too. And the amount of zoom is different, right? The 1. Okay, so this is different resolution, I'm saying. Right? This is the one at original resolution. That's the one I'm right at the wall. Right? Touching the wall and figure out exactly what's going on. This From now on, I'm going to say MRA, and you know it's going to be wavelength, okay? It's a way to represent signal in a multi-resolution setting. I'm going to discuss an example for 1D signal. We can generalize this to 2D later on. Suppose I have this signal. It's a piecewise constant signal. It will be 1, 3, 5, 7. Okay, so 8, 2, 8, 3, 8 is 1, 3, 5, 7, 7, so 4, 5, 6, 8, 7, 1. So at 6, 8, going down to 5. 7, 5. This is in time now, okay? That's a piecewise constant signal with 1/8 unit interval. Okay? The first thing I'm going to do is I'm going to represent it in multi-resolution. I will have a coarse approximation and the details. Is that clear? So tell me how to find a coarse approximation and detail for that signal. What would be a coarse approximation look like? Coarse, detail, okay? That's a detail, that's a coarse approximation. If you add together, you get back your original signal. Let's take average. I want to take average for coarse approximation, right? That's the easiest one to know. Take average and difference. Add together, you get the original signal, right? So what's the average of 1 and 3? 2. It is now a quarter. Average between 5 and 6, 7. 6. Put 2 quarter, okay? 7 and 7. 7. Right? 3 quarter. And 5 and 5. 5. Alright? I'm looking for a detailed signal right now. So that when I add them together, I get back my original signal. What's that detailed signal look like? Minus 1 and 1. Very good. Minus 1 and 1. And that's 1 quarter. And then minus 1 and 1. A half. And then the sum of these two get back to the original signal. Right? And furthermore, this is piecewise constant with 1/8 interval, right? What is that? 1/4 interval. The resolution change. Right? This way I get a coarse approximation, but not on the original scale. It's on the twice scale. Right? What's the next step? Do I work with this? I leave it alone. I work with that one. I'll take the coarse approximation. Right? That's what I'm doing here. Taking this. And we stop right now. Right? We leave this alone as a detail. We're doing this. Okay? So I'm taking this signal as my input right now. Go through the same process. Again, coarse approximation and detail. Right? So now I have taken that, decompose into coarse approximation plus detail. So what's the average of 2 and 6? 4. And this is 1/2. Average of 7 and 5. 6. 1. What is the detailed signal? So I'm working with this and this, right? What is it? -2 and 2? The other one is 1 and -1, right? Is that right? Any questions so far? What's the next step? We keep this. You can work one more time with that. Okay, so here is 5 and 1 and another one. Oh yeah. Okay? I want to give some names right now, okay? I want to name this V3, V2, W2, V1, V1, V0. Okay. What I'm doing here is decompose a piecewise constant 1/8 unit interval to a piecewise constant 1/4 and details 1/2 and details or 1 detail. So this way I have many ways to represent a signal, right? I can represent a signal at V3 only, which is the original one. Or I can have V2 plus W2. This is mean vector space. Okay? Right? Because I have V2, W2, V3. Or I can have V1, W1, V2. Right? Because V1, W1 is V2. Okay? W2 say the same. Or I can have V0, W0, which again give me V1, and then the other one. Right? W1, W2. This way I have 4 ways of representing a signal. Right? Each one at different resolution.
why more low? Because I think it's a bit normal.
This is meaning that the space orthogonal. I want to discuss the basis function. You can see that the space is orthogonal and the orthogonal. So when you add together, you expand the whole space. Okay. So look at this is V3. This is V2. W2. V1. W1. V0. W0. So let's look at the basis function for this space. Okay? What is the basis function for V0? How do you represent all signals with bitwise constant with unit interval? What is that basis function? Just 1 and 0, right? So let's go phi of t into the 1, that is 1. This. You will define basis function of t to be 1 like that. Then I can represent any signal with bitwise constant as the weight linear combination of this and shift. Right? If I have phi of t minus 1, and I go from 1 to 2, and so on. Is that clear? How about v1? What's the basis function for v1? Bitwise constant with half interval. It will be exactly like this, but scaling. So I have basis function to be 1 and v1/2. How do I relate this with that? It's phi of what? 2t. That's a scaling now, right? And the next one is what we have. We have a quarter. Okay? Be a quarter. And this will be phi of 4t. 2 squared. Right? 2 squared. 2 to the first power. That's 2. 2 to the 0 power. That's 1. And the last one will be 1/8. Right? That will be phi of 8t. That's 2 to the third. V3, 2 to the third. Okay? What is the basis function for W0? How about 1 and then minus 1? 0, 1/2. Let's call it W of t. Would that work? That's 1/2. Sorry. 1. That's 1/2. Would that go? Sure. This signal is what? Minus WT. Right? How about that basis function for this aspect? Exactly the same as this, but scale in, right? So you will have 1 minus 1. This is a half. That's a quarter. This is W of 2t. What is that signal in this? Minus 2 W of 2t plus 1 W of 2t minus 1. Right? 2t minus 1 shifted by a half. Because that's a 2t, right? So this is W of 2t minus 1. This is minus 2 W of 2t. Is that clear? Okay. Next one will be 2. This function is exactly the same before, but now a quarter. 1 and minus 1. So W of 40. So how do I represent that signal? Using that basis function. Minus W of 40 minus W of 40 minus 1 shifted back a quarter. It's 40, right? and this is 0, 0. Right? Okay? So what I'm doing here is I'm showing you all the basis functions associated with that this decomposition. Let's see which one is better. So V3, V2, W2, V1, W1, V0, W0. Tell me the coefficient of the expansion. V0. What is the coefficient here? 5. What's that coefficient? -1. Alright? How about this one? It will be 4, 6. Right? 4, 6. How about W1? -2, 1. Okay, now V2. 2, 6, 7, 5. How about V2? -1, 0. And V3, you know, right? It's 1, 3, 5. 1, 3, 5, 7, 7, 7, 5. Any of these that you choose have 8 coefficients. If you choose the first choice, V3, you have 8 numbers to represent that, right? And those are numbers that you use to reconstruct. Okay? If you choose the second choice, V2, but V2, how many coefficients do they have? 8. Right? 4 here and 4 there. It's still 8. Okay? If you choose the third choice, what do I have? V1 and these two guys. 2 plus 2 is 4. 4 plus 4 is 8. Right? The third choice, the last choice, we have 2, 3, 4, 5, 6, 7, 8. They all have 8 coefficients to choose. Which one is better? It's not the number of coefficients. It's how much change in the coefficient. Right? So let's think about, if you want to code. This has high and then grade. Look at this, 5, and then this is very, very small. Right? So if you use the third one, for example, if you have to truncate, right, or quantize, this is better than quantize. Because they're quite small. Okay? So if I'm looking at this one, right, you can think of this as, if you have a cost approximation, basically the average. It's 5. It's 5 plus 7 plus 5 plus 3 plus 1. That's together divided by 8. Right? That's the average. Right? That's what you how you represent. Taking the average first, and then you have the details coming in, right? You have this detail, that one, and this one. Depends on what you need to set. Okay? So if you only can see, in the low pass cost approximation, you might want to send only number 5. And that will be your signal to represent. If you need a high resolution, I want to send 5 and 5 and this coefficient. And give me this. I have 4 and 6 now. Slightly more details. It's not that good. It's good. With this more information, now I have to send this 2, right? 2 and 1. And I got this. More details now. Okay, more structure. If we need even more, then I'm sending, -1, -1, 0, 0. And I get back to this one. Okay? So this is basically multi-resolution. That's an example. You see all the basis functions associated with this. The nice thing here is that the basis function has scale. Right? They have phi of t. I only have to know phi of t and w of t. The scaling function is called scaling function, and this is called wavelets. For every dyadic wavelet system, has a scaling function associated with the low pass operation. There's a wavelet associated with the high pass details operation. And I only have to know two of them, P of t and W of t. Because the basis function for the other scale, the other resolution is related, right? P of t, P of 2t, P of 4t, P of 8t, and so on. And vice versa for W of t. Any questions? Which space is bigger? Which space is bigger than one space? I'm comparing the space, the span of that space. Who think V0 is bigger? Who think V1 is bigger? V1 is bigger, right? The V1 space is a space that captures half. This y constant with half unit interval. V0 is the whole unit interval. So obviously a half, you can build two halves, right? Become one. So where you can see that V1, V0 can be one, right? And so on. And V1 can be two. And so on. Okay? V0 and V1. What is the basic function of V0? P of t, right? What's the basic function in V1? P of 2t. Tell me how to write this statement using basis function. V0 in V1. Okay? I know that the basis function in V0 is P of t. And the basis function in V1 is P of 2t. How do I translate that statement using basis function? If I can represent P of t using a combination of P of 2t minus k, let's call this H naught of k. This is scaling, okay? If I can find a set of number H naught, so that this is true, then I'm done, right? It's saying that I can represent a basis function in V naught in terms of V1. It means that V naught in V1. Right? Because basically, if I know, this relationship, if you give me anything in V naught, I can plug into here, and I'm done. Right? If I know a signal x of t is phi of t plus 7 phi of t minus 3, what do? I take phi of t, I plug into here, right? I got something in phi of t minus k, right? I got t minus 3, I plug to minus 3 here, I got minus 3, okay, and so on. Okay, so it means that I can write x of t in phi of 2t. Okay? Alright. And how about W, 0, and V1? Which space is bigger? 0 is right here. Right? And V1 is right there. Which space is bigger? V1. W0 in V1. Which means that the basis function in W0, which is the wavelet W of t, can be represented as linear combination of the basis function in V1, which is P of 2t. This is called the refinement equation. It means that if I choose an H naught H1, and H naught here is basically the low pass filter in the filter bank. Okay? H1 is a high pass filter, just filter back. If you given H0, okay, the question is, can I solve this to get my basis function? And vice versa. Right? If you're given H0 and H1, can I find phi of t and W of t? That's an easy question, right? Just plug it into here and then compute it. And I will show you how to do it, tomorrow, for example. Right? The question is this true? That's a much harder question to answer. I will not go have time to discuss this. Okay? It's in chapter 7 of my book. If you're interested, you can read chapter 7 of my book, which discuss the condition on H, such that you can do this. Okay? All right. So, in 2 minutes, I'm going to discuss something else. Okay?
Excuse me.
Yeah. So if I have V3, right? What is the operation to give me V2 and W2? We kind of in hand waving saying that it will be a filter bank. Okay, you show me it's a filter bank. Let's go back to this, right? How do I get 2? Take the average. How do I represent average here? I filter 1/2, 1/2. And the difference here is 1/2 minus 1/2, right? Look at the first one and you can figure out the second one, right? Is that enough? No. Why? Why not? You have to downsample. Why do you downsample? Where's downsample over here? I never downsample. Or did I? What would be the output here if you don't downsample? What would be the input? What would be the output here if I don't downsample? I have 2, 4, 6, 7, 7, and so on. I'm not doing it for every coefficient. I'm doing it at the order coefficient. When I'm taking the average, I already downsample. I skip, right? 1 and 3. I skip 3 and 5. Okay? I'm doing 1 and 3, 5 and 7, 7 and 7, 5 and 5. If I don't downsample, I have to do 1 and 3, 3 and 5, 5 and 7, 7 and 7, so on and so forth. So this is already downsample. Okay? You didn't recognize it, but now you do. That's why you have to downsample. And that is when you have this multi-resolution. And you can show that this equation here. I put phi of t in here. Exercise is called, okay? Phi of t in here. This equation is basically this branch right here. So the first branch is the first equation. This branch here, the second equation. Okay? You can show this out. And there, so conversion of H naught to phi of t in that sample. So exercise 4. Any question? I think we end today's lecture. I take questions. Tomorrow I will discuss how to find phi of t, W of t, given the filters. And then we will